For fans, the thrill of driving an electric locomotive is undoubtedly in operating the master controller. Unlike modern electronically controlled locomotives, older locomotives like those from the Showa era had less power margins and less automation, resulting in a greater sense of tension. Especially before the advent of the EF65, engineers would carefully watch the ammeter, gradually advancing the master controller to avoid wheel slip and excessive load on the motors and resistors. For example, with the EF58, the master controller was advanced one notch at a time with intervals in between. When the master controller reached the fifth notch, the motor current would exceed 500 amperes. As the speed gradually increased, the motor current would decrease. Once the motor current dropped below 500 amperes, the master controller would be advanced another notch. The motor current would again exceed 500 amperes, reaching up to 600 amperes, and then decrease as the speed increased, falling below 500 amperes again. This process would be repeated. Naturally, these changes in current directly corresponded to changes in tractive effort. Each time the master controller was advanced, the tractive effort would increase sharply by about 300 kilograms, and in some cases, the fluctuation could reach as much as 500 kilograms. Moreover, these fluctuations occurred instantaneously with each switch operation, reflecting the high responsiveness of the electric motors. In contrast, steam and diesel locomotives, which had slower responding motive sources, did not experience such instantaneous fluctuations in tractive effort. Since their tractive effort depended on changes in steam or combustion pressure, the changes were relatively smooth. High-speed geared EF58 locomotives, with their lower tractive effort relative to their adhesion, rarely required concern about wheel slip unless multiple adverse conditions coincided. However, the lower gear ratio of the freight-oriented EF15 meant that it produced high tractive effort at low speeds, requiring careful judgment and operation to prevent wheel slip based on the condition of the rails. Moreover, since these locomotives were equipped with leading axles, if the rail surface was concave, a larger portion of the locomotive's weight was distributed to the leading axles, causing the driving wheels in the middle to lift slightly, reducing the weight on them. The same phenomenon occurred when transitioning from a curve to a straight section, as the cant provided on curves was no longer present on straight sections. Therefore, when stopping at signals or other points in such locations, the engineer had to carefully position the locomotive. Although three-axle bogies with two sets of 6 driving axles, as were common in electric locomotives of that era, were less susceptible to this effect than steam locomotives, caution was still necessary when operating at maximum tractive effort. In contrast, the EH10 locomotive, which did not have leading axles, did not suffer from this disadvantage. Furthermore, at the beginning of rain, dirt on the rail surface mixed with water, creating a film-like substance that significantly reduced adhesion. While it was possible to respond to clear weather conditions like rain or snow, leakage within tunnels was unpredictable. Engineers had to constantly monitor the surroundings, ammeters, and motor sounds to anticipate wheel slip, and they had to be ready to notch up or apply sand as needed. Once wheel slip occurred, the coefficient of friction would decrease sharply, causing a sudden drop in tractive effort. Moreover, at low speeds, the motors were connected in series, and as explained in a separate video, if one of the series-connected motors slipped, the circuit current would drop sharply, while the terminal voltage of that motor would rise rapidly, creating a vicious cycle that accelerated the slip. To restore the reduced coefficient of friction, the only option was to stop the wheel slip. The engineer had to notch back, confirm that the slip had stopped by listening to the sounds and monitoring the ammeter, and then notch up again to the maximum tractive effort without causing slip. Furthermore, for the EF15, which hauled 1,200-ton freight trains at the time, any uphill gradient left little margin for error. Controlling the electric motor torque to the brink of wheel slip was an extremely difficult task. Engineers had to constantly monitor the ammeter and rely on the sound of the motors to ensure that wheel slip did not occur with each notch up. Moreover, they could not neglect to check for safety hazards ahead and signals, making acceleration to a certain speed quite challenging. With the advent of new high-performance electric locomotives, this notch-up operation became semi-automated, allowing engineers to focus more on forward observation. The number of notches increased, and vernier control significantly reduced fluctuations in motor torque, greatly reducing the fear of wheel slip under harsh conditions. Furthermore, even if wheel slip did occur, the re-adhesion operation, which had previously been performed manually using the master controller, became automated, significantly changing the operability of the new and old locomotives. Although output increased, allowing tractive effort to be increased to the limit of adhesion, these new devices suppressed wheel slip. This significantly reduced the psychological burden on engineers. The EF66, the pinnacle and culmination of resistance-controlled electric locomotives in the JNR era, made its appearance and was active in hauling express freight trains. However, unfortunately, due to declining demand and the bankruptcy of JNR, locomotives as a whole entered a long period of stagnation. Amidst this situation, privatization was carried out to fundamentally reform the deteriorating JNR organization. The freight department was spun off into a separate company, and supported by a favorable economic climate, development of high-performance electric locomotives resumed. Unlike previous JNR locomotives, these locomotives were essentially electronic devices, and master controller operation was mediated by computers, greatly reducing the reliance on the engineer's intuition. It seemed as if an era had dawned where locomotives capable of unleashing world-class power without waste would be active. Unfortunately, however, the subsequent long economic stagnation led to a decline in transportation demand, and a decrease in investment in ground facilities meant that these locomotives never had the opportunity to demonstrate their full potential.